So hi everyone, I've just finished my cup of black coffee and this is going to be a tutorial on implementing backpropagation using neural networks from scratch using NumPy in Python. So I've essentially given here you a notebook that gives you a hands-on approach on building simple neural networks from scratch only using NumPy, which is a fundamental Python library known for array operations, numerical computations. And the focus here is to understand and manually implement the core aspects of neural network training, including forward propagation, backward propagation without relying on, TensorFlow or PyTorch. So we start with our necessary imports. And for this particular problem, for this implementation, I've chosen the iris dataset, which is a common classification problem in beginner data science as well as ML. So I've chosen this data set, and herein I've shown the scatter plot of the sepal width and the sepal length with respect to the various classes, which are setosa, versicolor, and vanzenica. So what we essentially want at the end of the model training to find separable boundaries between these classes, and by that I mean you would essentially end up with some separability of these data points which your model can use to classify them in various classes. So that's what we aim to do with our neural network implementation, which is coming right up. So here we will try to implement a simple neural network with one hidden layer using ReLU, softmax activation functions, and backpropagation for learning. So we start by initializing our parameters by defining a function called initialize parameters. And the purpose is to initialize your network parameters, which are weights and biases fundamental to a neural network, to small random values to prevent any symmetry in learning. And we have the function which has the input parameters of input size, hidden size, and output size. And for details, of course, you have W1 and W2, which are the weight matrices for hidden as well as the output layers, initialized with a normal distribution scaled by 0.01, which we have done right over here in this function. So as you can see, we also have the B1 and the B2 matrices, which are the bias vectors, which are initialized by numpy.zeros, and they are, of course, for the hidden layer as well as the output layer. So of course we need to define our activation functions here for this particular implementation. We have ReLU, softmax, and we have defined these functions, which are simple enough mathematically. You have the ReLU z, the ReLU derivative z, and the softmax z. So z is essentially your output matrix by the end of the model training that you get. So of course you need a method for forward propagation, which is implemented here, which takes in the input parameter of x, which is the input, as well as the parameters which we defined over here, and it will take the parameters over here, compute z1 using np.w1 and x1 plus the b1, and a1 will be the ReLU activation on the z1, and z2 similarly will be np dot w2 and a1, which is additionally essentially f multiplication using a weight and addition using a bias value. And you have the softmax activation, and what we end up is a dictionary which has z1, a1, z2, and a2 returned, and of course we return a2 as well as the cache with the forward propagation method. And of course we need a cost function to calculate the cross entropy loss, in this case for a2 and y, which we will get, and essentially try to minimize this cost. So backward propagation is the necessary part and the key part of this implementation here. So the purpose is to compute gradients necessary for learning the parameters by gradient descent. So we essentially compute the gradients, and we define the function with parameters cache x and y, and of course the outputs of this function are given in this dictionary, which are your essentially dz1, dw2, and db2, which are the gradient loss with respect to the output layers, weights and biases, and dz1, dw1, and db1, which are essentially your gradient losses with respect to the hidden layers, weights and biases. So of course now we want, since we've calculated these matrices, we want our W matrices, weights and biases matrices, which we had initialized over here, to be updated using the gradients we've calculated. All of these need to be fed back into these so that the backward propagation can be implemented. So we define the update parameters function over here, which takes in inputs of parameters, gradients, as well as your learning rate. So it will essentially adjust the parameters W1, W2, B1, B2 using the gradients computed in backward propagation. And here is the function. So you essentially take the W1 matrix and give it a negative value of subtract from it the learning rate into the gradient dW1. So you essentially feedback your gradients which you got from the output layer and use it to factor in as a direction that the model should not go to minimize the cost function essentially. So of course we have the model method implemented over here, which has the inputs of x, y, input size, hidden size, output size, number of iterations, as well as your learning rate. And the parameters is essentially the initialized parameters that we had implemented right over here. We start by loading this, and for our given input size, hidden size, and the output size, which can be defined from this model inputs. And what we essentially do for I in range of number of iterations the model is going to be trained for, we do a forward propagation first with x in the parameters, which are the initial parameters which we had initialized. And once the forward propagation commences, you essentially get an updated Z1, A1, Z2, A2 matrix calculation. And if we go back here, so we can compute the cost with regards to this iteration. We calculate the gradients from the backward propagation method we had defined earlier, and we update the parameters using the update parameters function we had over here, and you return the parameters. And of course you need to calculate your predictions as well as the accuracy. So predictions being outputs of the neural network training into your classification inputs, as in where a particular data point lies with respect to its class. So essentially what this function over here does is takes in x as well as the parameters and performs a forward pass using the trained network parameters and computes the output predictions for the input data x. And it returns predictions, which is an array of predicted classes for each label in x. So essentially you have a prediction of classes. And of course we want to see how accurate our model was, so we define an accuracy function which basically takes a mean of the predictions which were equal to the classes they should have fallen into. And of course the updates we make during the backpropagation step of the implementation, I intend to store them to later on see or maybe visualize how our backward propagation helped improve our model accuracy over iterations. So this store updates function collects and stores the norms in of the weights and biases as well as the gradient norms at a given iteration. So this is very useful monitoring and debugging, and it essentially returns an update info dictionary containing the norms of parameters, the gradient norms, and the iteration number. Then of course we have the model which we try to train over here. So I have implemented it again over here just to have our store updates method incorporated into the model. So this is a re-implementation. If at any point you feel you want to try and implement this on your own, feel free to do so, or you can click on copy code option over here for any of the code blocks and see like if your implementation matches the result we are trying to achieve. And we do the model training and essentially get us the values of the train parameters, updated records, and accuracy records. And for all of this process, I intended to make it more clear with the help of some visualizations that can help us get us more a deeper insight into the intricacies and the advantages and the process of backward propagation. So this is in model accuracy over iterations plot. On x-axis we have the number of training iteration indicating the points in training at which the model's accuracy is evaluated, and y-axis you have the percentage accuracy measuring how well the model predicts the correct classifications or the validation set at the end of a particular iteration. So here is your line plot. So as you can see, at the starting the accuracy was somewhere over 30% and it gradually grew to over 90%. So that's how our model accuracy improved with the incorporation of backward propagation. And I also did a visualization of parameter and gradient norms over multiple iterations, how basically your norms and the gradient norms got updated over multiple iterations of the neural network training. So as you can see, so essentially we come to the end of this notebook, this tutorial. So we want to see how our model performed. So we use some standard metrics like model accuracy, confusion matrix, precision recall, and F1 score. These are pretty basic to supervised, unsupervised learning. If you've delved into those projects, especially for supervised projects, like logistic regression, if you've done, I'm sure you're familiar with precision recall, F1 score. If you're not, please feel free to dive deeper into them, or you can just refer to this write-up over here. I think it can be helpful to explain the concept and drive the point home. So essentially what I've done here is try to print all of my confusion matrix, precision recall, F1 scores, and you can see how this code is implemented. Maybe copy it, run it in your local environment, or try to build it on your own, which is the best always. So here is what we get. So our model accuracy on test set ultimately was 96.67%. This is the confusion matrix, and we of course have the metrics per class. So for Setosa class, precision was 100%, recall was 100%, versicolor 100%, 88% recall. Virginica, precision is 91% and recall is 100%. So you see you get above 94% F1 score. So this is a basic implementation of a neural network training using backward propagation. Fairly simple to implement, fully spelled out in code over here. And that was my intention, to distribute my learnings in data science. In under 15 minutes, I tried to cover everything about backward propagation. I would really urge you to go through the notebook, which I will provide in the links, and see how do you like it. And the goal really here was to drive the point home that if your fundamentals are strong, you can have a very great expertise in a particular field. So that was the goal. I hope this video was helpful. Thank you so much for tuning in, and I will hopefully see you in the next one. Thanks.